Okay, I'm glad that you're back with us, and I don't think I even moved anything, so you should be able to pick up right where we left off here. So, let's see, we have time in hours and temperature. Let's see, we're starting at 70 degrees. That's what I keep my house. So at 0 hours, we're at 70 degrees. Now, after 1 hour, our temperature decreases 10 degrees. That's what the problem says. So it makes sense that after 1 hour, we're at 60 degrees. After 2 hours, we're 10 degrees colder, so we're at 50, so on and so forth. At 3 hours, we're at 40. At 4 hours, we're at 30. And by the way, sorry about the person who walked behind me earlier. Um, okay, anyways, let's see. So what is our rate of change? Rate of change is the change in y over the change in x. Change in y, let's see, let's go from this point to this point. 60 to 50, 60 to 50. Change in y would be a negative 10, right? And for the corresponding x coordinates, we go from 1 to 2. 1 to 2. The change in x is from 1 to 2, so that's 1. So our rate of change is 10 degrees, negative 10 degrees over 1 hour, which is going to be negative 10 degrees per hour. All right, pretty simple, right? Not a big deal. Moving on, very closely related to that is our direct variation. And again, I really hope you can see everything. Direct variation is a special type of linear equation where the line passes through the origin and represents a proportional situation. All right, so for example, let's look at y equals 2x, okay? Y equals 2x. This is the line of y equals 2x. Now, does it pass through the origin? It does. Check. All right, now does it represent a proportional situation? Well, let's talk about that. We can determine that by setting up a t-table. And for some reason I have x's on the right side and y's on the left. But anyways, you can follow. So whenever x equals 1, substitute 1 in for x, y would be 2, right? When x is 2, y would be 4. When x is 3, 2 times 3, y would be 6. So do we see a pattern here? Indeed we do. The y's are basically double the x's. So y's are double the x's, and we call that, with respect to this, proportional. So this indeed has a direct variation. It passes through the origin, and it is a proportional situation. Okay, great. So, yeah. So in this equation, which is y equals 2x, we call the coefficient of x, the coefficient is the constant on the variable, in this case the constant on x, we call this coefficient the constant of variation. And if I can let you in on a hint, the coefficient of x is always the slope of the equation. Pretty cool, huh? Anyways, let's see. So for this, y equals 2x, the constant of variation is 2, which is exactly what we saw in our t-table up here. Let's see, x differed from y basically by doubling it. So when x was 2, y doubled it. When x was 3, y doubled it. That's the constant of variation. And we call this y equals kx. Now I know constant starts with a c, but in math we call it k anyways, so don't tell Mrs. King about that. She'll be angry. But anyways, k again is the constant of variation. So for another example, y equals negative 6x. Negative 6 is the coefficient on x, so negative 6 is our constant of variation. Okay, very last thing. Yeah, very last thing. Cool. All right, now, all right, first off, I know I'm talking really fast. The reason why I'm doing that is to get through this quickly and use less video time. One thing that you can do, though, is replay the videos several times if you don't understand a concept. And you probably would anyways, just because you love your pre-algebra teacher, right? Awesome. Great. So anyways, back to this. Very last concept. We're still talking about the constant of variation. And it's really easy to find it whenever it's given here right in front of you, right? Oh, negative 6. Easy. But what if we aren't given that? Let's take an example here. Let's say tonight it's going to start snowing, of course. Let's see. So, just like what we did right here, it can be represented in a graph here. Here we had time in hours as our x-coordinates, and then temperature was our y's, except for instead of temperatures, we're going to do the height of the snow. So we're going to have inches as our y coordinates. So back here, we have time in hours, that's past, as our x-coordinates, and height in inches is our y-coordinates, okay? So let's see, after 1 hour, let's say it snows 1.75 inches. Bam. After 2 hours, it snows a total of 3 inches, okay? After 3 hours, we have 4 inches on the ground. Bam. And lastly, after 4 hours, we have about 5.9 inches. Okay, so we don't have a constant of variation yet. But how could we find the constant of variation? Well, remember what this equation was back here. I bet you could figure this out on your own. We have y equals k times x. Now, what if I told you to solve for k? Well, you would ask yourself, what's happening to k? Because I want to get it by itself if I'm solving for it. So it's being multiplied by x. So to undo that, we would divide by x. So we would have kx divided by x, the x's would cancel out, equals y over x. K would equal y over x, which is exactly the equation that I was going to give you right up here. So k, again, is the constant of variation, equals y over x. So when we don't have the constant of variation, this is how we can find it. Take our y value and divide it by the x value. So for here, we would have 1.75 divided by 1, pretty simple, 1.75. Here we have 3 divided by 2, pretty simple, 1.5, so on and so forth. Now you'll see that our constant of variation isn't always the same, but we can estimate. You know, snow doesn't always fall at the same rates. So we can estimate this. This is all about 1.5. So we're going to call our constant about a 1.5 is our constant of variation. So we might see some questions like this about how much snow will have fallen after 6 hours. Well, we just plug in the information where we know it should go. We said our constant of variation is about 1.5, so we would have y equals 1.5x. Like I said, the constant of variation is always the coefficient on the x. So y represents the height in inches of snow, and that's what we want to find out, right? So we don't know what that is, so we're going to leave it y. X is the time that's passed, and we do know what that is, right? Because it's asking after 6 hours. Bam, we can just substitute that right in. So we're going to have y equals 1.5x, substitute the 6 hours, y equals 1.5 times 6, y then would be about 9 inches. Yeah, there you go, about 9 inches. Great, so that's how we can do that. Now again, if I went too fast for you, please just watch this over 2, 3, 10, 20, 30 times. And if you still have questions, just email me and we'll work through it. So our homework is going to be on page 396, 9 to 23. And for you visual learners, we are not doing 13, not 13, or not 21, okay? So no 13 or no 21. All right, cool. So just so we know that we have this, let's do an example. So press pause, get out your book, then unpause. All right, great. So we are on page 396. Let's look at number 14. The directions are suppose y varies directly with x. Write an equation relating x and y. So for 14, our y is 8 when x equals 4. And remember that equation that we talked about, that k equals y over x, right? Great, so let's put our y value over our x value. So k would equal 8 over 4, which would be 2. And then we just substitute that back in, so y equals 2x, because the 2 is the coefficient on our x. So our answer would be y equals 2x, 2 being the constant of variation. And lastly, let's look at number 9. 9, find the rate of change for each linear function, which is the change in y over the change of x. The change in y goes from 0 to 12. The change in x is 0 to 1. So we would have 12 over 1. Let's keep our labels. The change is 12 inches per 1 foot. Pretty simple, right? Okay, we'll have fun. Again, email me if you're confused, and yeah, peace out.